Okay, so the sixth and the last. So let's see how much we can cover. Hopefully, we'll go into some aspects of many body chaos. But okay, so I was showing you some eigenfunctions of the standard map and the Baker's map, which should be thought about as eigenfunctions of single particle systems, but nevertheless shows all the complexities of quantum chaos and quantum chaotic eigenfunctions, which come in a bewildering variety. And they can be scarred by periodic orbits or other classical orbits, as well as be looking like random states or random waves superpositions. So I'm going to go into the second aspect first about random waves. I mentioned a little bit about scarring. I'm going to go into the statistical aspect of uh, considering it as random. I've already mentioned Berry's conjecture, but I'm going to make it more concrete for finite dimensional systems, and what exactly one means by a random state, and how good an approximation or how good a model is this of quantum chaotic eigenstates. So that's the first task that we're going to do. But before that, I need to talk about symmetries. And one of the, so there are two symmetries, two types of symmetries, unitary, anti-unitary. We are used to mostly unitary symmetries like, some kind of geometrical symmetry of parity or rotation and so on. And the anti-unitary symmetries are usually associated with time reversal symmetry kind of situation, but it can be some generalized anti-unitary symmetry. So an anti-unitary symmetry is prescribed by some operator like this. So a canonical time reversal, for instance, is freezing position and reversing momentum and going back in time. So what it actually means is that if you go forward in time for a time t and then reverse the motion, which means that invert the sign of the momenta, this is the same as first reversing the momentum sign at time 0 and then integrating back in time for a time t. These two states should match. So then you will call such a system having a time reversal symmetry. Now, one can see quite easily that such an operator which implements this in quantum mechanics cannot be linear, because it has to leave all the position eigenstates unchanged, because Q is going to Q. And if this is a linear operator, then that will imply that this operator is identity, because any operator which is acting on a complete set, if it fixes that set, then if it fixes every member of that set, then it's identity. But on the other hand, it's going to change the sign of momentum. And therefore, it has to have this peculiar thing that as it is acting through states like linear combinations, it has to complex conjugate these coefficients here and then act on these states phi 1 and phi 2. So this is said to be anti-linear. And for instance, just complex conjugation in position representation is our usual time reversal symmetry. So T acting on psi is psi star. Now this doesn't have a meaning unless you specify a basis, which is the position basis. So that's the usual complex conjugation. But a more general time reversal is any anti-unitary symmetry, and that is implemented in a form of a unitary operator or unitary matrix followed by conjugation, this complex conjugation operator. Okay, so Hamiltonian is said to be time reversal symmetric if it commutes with such a thing. Since we are interested in Floquet systems, what does it mean? You can just read this off from this top line. If you go forward in time, that is, this unitary operator is taking you forward in time now. This unitary has nothing to do with this unitary. This is time evolution. And then you do an anti-unitary operator on that. If that is same as doing the anti-unitary first and then going back in time, you inverse, then you would call that Floquet operator as having time reversal symmetry. And bosons will have, if you operate twice on this, will give you a sign of +1, fermions will be -1. So we'll be mostly concerned with the bosonic case. In bosonic case, it implies that such a symmetry, that is UK square equals +1, implies that this unitary here, which is implementing this anti-unitary symmetry, is a symmetric unitary. So U transpose is U. And you can see that you can change a basis so that the Floquet operator is also symmetric. So you may think about a unitary operator as having some general time reversal symmetry if under some basis change that operator is symmetric. Not only is it unitary, it's also symmetric. So symmetric matrices have real eigenstates, and therefore time reversal symmetry, and this is really the punchline if you don't follow all of that, time reversal symmetry implies that the eigenstates are generically real. If you just diagonalize it in any basis, it might come out to be complex, but even that basis can be time adapted so that the eigenstates can be real. So that statistical properties you should consider as if the state is real. In fact, for the students, most of the eigenstates that we calculate in textbooks, whether it's harmonic oscillator or atomic hydrogen atom, they're all real because they all have time reversal symmetry. Yeah, it's actually spin half integer. Okay, and so we can ask, what is, suppose our state is suppose our Hamiltonian or unitary operator is time reversal symmetric, then let us say that the eigenstates are real in that case, or they are typically then real. How can we describe these eigenstates? So you can take a basis which is time reversal adapted, and in that these coefficients xj, which is this eigenstate of that unitary operator, will be real. By the way, this is also true for a Hamiltonian system, so this need not be Floquet. If you take any Hamiltonian which is time reversal symmetric, calculate its eigenfunctions, it will be real, and these will be real numbers, xj. Now, what is the statistical characteristics of xj? We know that it is normalized as a state, so if you sum up xj squared, it is 1. If this is the only constraint, then you will call that a random state. And so here is a joint probability distribution of the amplitudes of the state psi, x1 to xn. There are n is the dimensionality of the space, so there are n components. If the joint probability of this is simply delta 1 minus sigma xj squared. So it is uniformly distributed on a sphere, on an n sphere, if you wish. Okay, so on a real n sphere, if it is uniformly distributed, then that will be an example of a random state. So you may think about this as a definition of a random state, that nothing else matters except its normalization. For those of you who have done statistical mechanics recently, this would be like actually the microcanonical distribution where of a free particle or an ideal gas, where this xj is replaced by momentum, because sum of the momentum square is the energy. So if you just divide by the energy, you'll get this. So this is looking like microcanonical ensemble. So this is just normalization constant, so that the integral of this over all these x is 1. You can integrate out n minus 1 of them and just ask what is the probability distribution for a single amplitude. You take a single amplitude and find out its histogram. It's distributed then in a normal fashion. Again, from statistical mechanics analogy, we know that the momentum distribution is a Gaussian. That is the Maxwell-Boltzmann distribution. So this is precisely the same physics. You can do this exactly. This is asymptotic for large n. You can also find out for finite n. But actually, n doesn't have to be very large. Practically, you can see that for n is 10 or something, it will be an excellent normal distribution. And there's only capital N, that's the number of states in this, which is a parameter. So, so the variance of, so it is 0 mean, and the variance is going as 1 over capital N. So now, if that is the model of a state which is random, what can we say about how spread the eigenfunctions are? So there are many measures of localization. Here is a very simple one. It says that if you sum over the amplitude to the power of 4. If you sum over the amplitude square itself, you'll get exactly 1. If you do to the power of 4 and you sum up over all of them, then that is called the inverse participation ratio. You can take an average of this so that you are doing an average over this ensemble, and you can calculate what that is. So there are n of these, capital N of these, and each one of them is distributed according to this P1x. So this is simply this integral x1 to the power of 4. This can be easily done. So for large n, the inverse participation ratio is 3 over n. What is the meaning of this inverse participation ratio? It means that the inverse of it, which you can call the participation ratio, is 1/3 of n. And it means that a real random states are such that only about 1/3 of the components are significant. After all, if you have an n-dimensional state, n of them can be real and n of them can be significant. So all of them can be 1 by n, for example, or 1 by square root of n, so that the normalization is preserved. But here it says that, so in that case, all the n of them are significant. But it says here that actually if you take a random state, you will find that only 1/3 of that is significant. So this, you should think about this factor 1/3 and this factor 3 as a quantum effect, because classically these things would be just spread out, uniformly. So here I'm showing you, I've introduced already the standard map, so you can play around with all those parameters there. I've taken n is 200. And what I'm doing is, for every value of k, I'm diagonalizing this. I get 200 eigenstates. For each of those eigenstates, I have these xj. I'm calculating xj to the power of 4, and I'm getting a number, and I'm taking 1 over that, and I'm averaging that over all the 200 states. Okay, so ultimately, I have only one number from all the 200 states. I plot that as a function of this parameter k. Remember that k, as k grows above 5, there is a transition to chaos. K equal to 0 is integrable. And if you notice here, I haven't said anything about this basis. One assumes that this basis, this statement is independent of the basis. That you see, its typical statements are independent of the basis. So here I've taken two bases. This will be momentum basis, this red one. And you can see that in the momentum basis, it's starting from a low participation ratio. That means that the states are highly localized for small values of k, that is near integrable regime. And then it grows, and then it fluctuates around this. This line is 1/3, you can see, 0.33. It's fluctuating around that. Remember that the fixed point loses stability at 4, and after that, most of the things are chaotic. And this is for the case of the state in the position representation. You see, it's completely delocalized. It's starting from very high participation ratios. It's decreasing, and then it's again oscillating around this 1/3. So you would expect random states to be valid in the regime of quantum chaos. Yeah. And this difference is easily understandable because, remember, if we go back, you can see some of these eigenstates. These are eigenstates in the phase space representation. So let's take some state like this. This is position horizontally, momentum vertically. You can see that it's not spread out in momentum at all. It's more or less localized in momentum, and therefore its participation ratio is very small. Whereas if you take position, it's spread all over the position, and therefore it's delocalized in position. So, but it doesn't matter once chaos sets in. Both of them tend towards the random state value of 1/3. Yeah. Yeah. Not dimensionality. This is valid for any dimension. That is, the 3 is coming from the fact that it is real symmetric. You can kind of probably think about it as maybe something like in the analogy to the Maxwell-Boltzmann gas, right? You have 3 directions that way, but actually it's not related to that also. Maybe that's not a good analogy. No, the 3 is not related to dimensions. You can take any many particle system, whatever it is, you will get 3. No, nothing. Because you see, This doesn't have any such information. It just says n is the dimension of the Hilbert space. That's all. Okay. Yeah. Yeah, yeah. In that case, you will get different numbers here. Okay, for the IPR, you get 3 inverse participation ratio, which has a good interpretation of the participation ratio as being this. There are many moments and entropies that one can calculate. I'm calculating the simplest. Good question. So we want something whose inverse will tell you roughly like how much of it is, how much of the states are localized. So I can give you a very rough, analogy of, let's take a state which is everywhere delocalized. You will get 1 by root n as this xj, right? So if you calculate this, you'll get 1 by n squared, x power 4, times n. So you'll get 1 by n. And the inverse of that is n. And all of them are occupied. If only one of them, it's highly localized, then there's only one which is 1, everything else is 0, and you'll get this to be 1. So if that convinces you, that sort of, the extreme cases, you see that it's exactly the number of levels. Otherwise, it's approximately that. Okay. This is something which is used widely in all parts of physics. This inverse participation ratio is related to also some things which people call correlation dimension and so on in classical physics. Okay, now what happens if the states don't follow time reversal symmetry and you break time reversal symmetry? In which case, the states are typically complex. But now these coefficients, let's call that z to zn, you have n components that are complex. The normalization is modulus zj square is 1. Again, you declare that that's the only constraint, and that will be the joint probability distribution of these n complex numbers. Each of them has a real part, imaginary part, xi, yi. And you can look at the intensities, Ti, which is the sum of these. And then it is simply uniform on this simplex, that is sigma Ti equal to 1. It's a delta function of 1 minus Ti. So if you look at the intensities, this is the exact distribution for a single intensity, which you can see is going for large n very quickly to an exponential distribution. Okay. This is the intensity, remember, it's not the amplitude, it's the intensity. So if you want the corresponding thing for this, you have to find the distribution of x squared, which will be one of the chi-square distributions. Here, this is also a chi-square. It's a pure exponential distribution. Nothing can be simpler. And you can scale this. You take an intensity, a single intensity, multiplied by the dimension. That will be of the order of 1. Because, again, the intensity, you've already squared it. So it will be of the order of 1 over n. So if you multiply by n, you get a simple e to the power minus t exponential distribution. Both of these kind of distributions are called Porter-Thomas distributions. And in this case, the inverse participation ratio is just t squared because already you have taken a square for the intensity. So this is the sum of Ti is 1. So sum of Ti square is the IPR. And from this, again, for the large n, you can find 2 by n. So you see that unlike the participation ratio, therefore, is n by 2. So complex random states are such that about 1/2 of the components are significant. The real symmetric or time reversal case, you had 1/3. You have more delocalization happening because of the break of time reversal symmetry. You can use the same standard map model, for example, to verify these kind of things. So you can put a phase. I introduced this Aronow-Bohm phase. You can introduce that flux and break time reversal symmetry. I've done that here as a function of k. Again, you can see that and here I have also various n dimensionalities. So position representation, momentum representation, n is 100, 200, 400. I've divided it by n so that now you can see that for large k, after chaos is set in, it's about 1/2 rather than 1/3. It's in fact a pretty decent 1/2. And again, at the intermediate regime and integrable, near integrable regime, it deviates from these standard states in very interesting ways. and it is basis dependent. Momentums are more localized than the position. Yeah. Single particle? Yeah, these are all single particle. This is all like you have just one oscillator or one rotor that's being kicked around. Single particle. But all of these things are true for many particle also. That comes in the symmetry classes. So you will have, there is another class called for the fermions, you have not just complex, you have quaternions actually as your states. Okay, so you have some kind of quaternion symmetry which is going on. I'm not going to talk about that at all, but you can actually implement it also in the standard map. You can have a spin half kind of standard map and see that. That's the symplectic ensembles. I'll come to some of that, but I won't really go into the symplectic case. Okay, so unitary symmetries we are more familiar with, things like parity and so on. You need to reduce this. For example, here I've taken for the standard map phase of 1/2. This will respect exactly a parity kind of operator which will reflect a position state or momentum state, by the way, about the center. So about n/2, and the square of that is identity. So you can always symmetry reduce states which are exactly symmetric into positive symmetry and negative symmetric states, and you can block diagonalize a unitary operator or a Hamiltonian into parity sectors. Now let us take, for example, the standard map itself and as a function of k. So in fact, it's this unitary operator. I'm diagonalizing, finding out the eigenvalues. The eigenvalues lie on the unit circle. It's a unitary operator. We'll take these eigenangles. They'll be like quasi-energies. They are our equivalent of energies. They are real numbers. We will plot them as a function of k. And for a given value of k, you have n/2 eigenvalues for a given symmetry reduced sector. You have exactly n/2 positive parity. You have n/2 negative parity. So here I've taken n equals 30. So you have 15 states which are positive parity, 15 states which are negative parity. I'm simply plotting them eigenangle. They go from -pi to pi as a function of this k. Okay, so you see again quite a different scenario for k smaller than 4 when about it's a kind of a mixed phase space to something here k much larger than 5 where there is chaos. What do you see? You notice that here you have things which are looking almost like crossings, and also you have very large curves, kind of you can follow curves around for some time. There are these straight lines kind of streaking out like this in this. After 4, they kind of, all of them give way to more or less these kind of constrained kind of random walk motions where there are only avoided crossings. They come close by, they typically come close by, they will avoid each other. There will be a gap and they will avoid. Even here, if you look closely, this could be a very small avoided crossing. So a lot of crossings here for small k and large k, you have these avoided crossings and this kind of. So this is the parity, negative parity negative parity sector. It's almost the same picture. You need to separate out the parities because these parities are independent. If I plotted all the 30 together, you will find a lot of intersections here also in the chaotic region. That's because these two parity sectors are moving independent of each other. There's no interaction between them, and therefore they will give you some idea as if there are level crossings. But that's not true. Each of these levels are belonging to different symmetry sectors. So you should. Okay. So I was curious, so we do this and then we see these straight line kind of objects. What are they? Okay, what kind of states are they? So I just took some particular k, which is 3, and then these are all the eigenangles corresponding to 3. Okay, so I find the eigenangle which is lying on the straight line here, that is this. And similarly for this parity sector, I find out where it lies at k equal to 3, that is this. And although I haven't marked it here, this is all the eigenfunctions. So there are 30 eigenfunctions in the coherent state representation for this case. And what do you think? Where do you think these states are? This state and this state. Any guesses? The state and this state. Which of the states in this belong to this? Well, you know, it's kind of common sense questions. Which is the odd man out kind of questions, right? So the odd man out are clearly those which are highly localized here, right? So there are these states, and in fact, these states here correspond to these states where k is 3, the fixed point at the origin has still not lost stability.
So you mean these are all K3
Yeah, this is all k equal to 3 eigenstates. I just took them, all these dot. So there are 30 of them. Each one of them corresponds to one dot, either here or here. All the states are there. And actually this state and this state, yeah, these two states correspond to these states. And it's not, again, these are highly localized states which are influenced by stable orbits, and they are the ones which are responsible for these things. And in fact, the slope of these are called level velocities. It is how much your levels are responding to a change in the parameter. That's a very important quantity. Actually, in metrology these days, this is a very important quantity. If you want to measure some magnetic field or something like that, you want to see any change in the magnetic field, your system should respond very fast, very quickly. So these kind of states can be used for these objects. So there is a whole theory about level velocities and so on, which I won't go into, but I just wanted to point out that these also correspond to states which you can visualize like this. Not necessarily always. And in this case, yes, one can see quite easily, because it more or less is an expectation value of, you see, this cosine is what is in the potential. So it's like a Feynman-Vernon kind of theorem, the rate of change of the rate of change of energies is some expectation value of an operator, which is here that operator is essentially cos theta. Cos theta is peaking at the origin. So if you have some fixed point at the origin, it will be large. And that's sort of essentially why these things are coming. Level repulsion is happening here. You have level repulsion, yeah. Of quantum, that's one of the important things. I'll come to that. Okay, so let's move on. So in fact, I'm coming to level repulsion. So this is just one slide. I'll come into some more details of random matrix theory in the next half an hour. So this is one way in which people are looking at, as Kiran was saying, level repulsion. So you look at all these energies, right? And then you ask at the gaps, nearest neighbor gaps. So there seem to be more small nearest neighbor gaps here than here maybe. So let's look at the nearest neighbor gaps and see how they are distributed. Again, you have to separate out positive and negative parity. First do that. So this was first done by Bohigas, Giannani and Schmidt, almost probably first done. For the case of billiards, they did this first, this kind of analysis. So they took a stadium billiard, they parity reduced it, and they found all the eigenvalues numerically, and they plotted this. This is for actually the circle billiard, and this you can this is essentially coming from some zeros of the Bessel function or something, right? The circle billiard eigenvalues. If you do the nearest neighbor for that, it turns out to be an exponential minus s. I am saying unfolded here. I'm not going to go into the detail of what unfolding is, but I'll just say that unfolding is a procedure which is a mapping of the energy levels, one-to-one mapping of energy levels to some bunch of numbers such that the mean spacing is 1. Okay, so because you can have all kinds of systems, hydrogen atom, whatever, very different kind of atoms with very different energies. How your energy has a so you will want to keep some to compare different systems and to compare with universal quantities. So one unfolds it so that the mean spacing is 1 unit, and then calculate this. You will find e to the minus s as a distribution for this. Whereas if you do for, actually it's written here, Sinai billiard, I think. Sinai billiard, which is this billiard here, you do a symmetry reduction of this, and that is this. So you look at it as if there are boundary conditions which are appropriate boundary conditions on the small sector of this, and then you calculate the energy eigenvalues. Then you find that the spacings have a very different distribution like this as opposed to this. So that has a distribution which is vanishing at the origin, which tells you that these levels are not clustering close by, they are repelling each other. So in fact, they follow a Vignyana surmise, so-called Vignyana surmise very well, which is what is plotted here. So there is numerics and there is this. And so there is a very different behavior for integrable systems which are quantized and chaotic systems which are quantized, even in the energy levels, how they are spaced. The spacing of the energy levels, they repel if it's a chaotic system. So more recently, people are not unfolding because it's probably pain in the neck. So this is a more easier thing to do. They just take a ratio of successive spacings even without unfolding. So this can be the raw eigenangles or raw energies. So successive spacings, and then they calculate the average of this. This average, again, it can be average over many levels. Okay, many bunch of spectrum. And then for integrable systems, it turns out to be 0.39. That is, this is called a Poisson distribution. And if it's chaotic, it's very different. This is time reversal symmetric chaotic, it's 0.52. If it breaks time reversal symmetry, I think it's around 0.6. Maybe somebody remembers better, but it's something around 0.6, maybe more than 0.6. So you can very clearly distinguish integrable, chaotic, time reversal, chaotic, non-time reversal. So statistical properties of quantum chaos seem to be those of random matrices. So these are all derived from random matrix results, things like Vignyana surmise. And therefore some universality emerges. Eigenvalues of quantum chaos appear as strongly correlated random variables. I've already said something about eigenfunctions. That is, they are distributed statistically like this. So this is also correlated, but I would say it's weakly correlated because the only correlation is this, sum being 1. There's otherwise, it's, you might as well use this single particle, single intensity distribution to do a lot of things. You can get away with that. Whereas for eigenvalues, they are much more fewer in number, and actually they are much more correlated, and they are strongly correlated random variables. So their model is that of a more different kind of random variables than the eigenfunctions. Okay, so this is just to give you an idea of how these levels are for different kind of things. It's from some kind of a report by Bohigas and Giannani long ago. So if you just take random numbers between some independent random numbers, between some things, and you just put it down here like a barcode like this, you will get some bunch of numbers like this. Since they are completely independent, you have no control, you may find two of them to be very close. Wherever they are very close, there is a V kind of thing marked. So they are very close here. You can prescribe some less than something. You can have some mean spacings. You can say less than 0.1 mean spacing. Okay. Prime numbers. If you take prime numbers, put them up, they also look kind of random. Okay, so here you have 2 and 3, I guess, 5, 7, 11, 13, and so on. So, where you have twin primes are every consecutive odd integers are primes, so you have very close prime numbers. Okay, so that looks almost like random numbers. Now, if you take a nucleus resonance of a large nucleus like erbium and look at the resonance spectrum, you get something like this. So, in fact, random matrix theory was developed in the 50s by Wigner, Dyson, and Mehta to account for nuclear spectra like this. Statistical theory of nuclear spectra, not for quantum chaos. They were thinking about a nucleus as some complicated many body system. And they said, we don't know the Hamiltonian and so on. And therefore, we look at it as random matrices, and the eigenvalues which follow from that seem to describe actual experimentally obtained resonance spectra like this. But you can see even from this that there is a difference. The number of levels which are coming close by is very few compared to this. This is the Sinai billiard, which we just saw. So it's not some complicated many body thing. It's a single particle, but in a chaotic cavity. And these are the eigenvalues. Again, you can see that the close by spacings are few. They look more like this than Poisson or primes. They are fewer in number. The zeta function, the Riemann zeta function, there is still unsolved problem there lying there. And the zeros of the Riemann zeta function, I'm not going to go into it. It's a fascinating topic. But it appears that if you plot the zeros of this, they will also look kind of random. And actually Riemann studied the zeta function so as to understand the density of prime numbers. So there is a deep connection between these two things. But you can see that the zeros of the Riemann zeta function almost have there is no V marked at all. So it's quite level repulsion or zero repulsion is very strong here. And if you look statistically at this, it looks like that of a time reversal breaking quantum chaotic system, whereas the Sinai time reversal is preserved. So in opposed to this is a harmonic or uniform. Uniform, all the levels are away from each other exactly. So what kind of thing is being said here is, if you look at a chaotic system with time reversal symmetry, like a Sinai billiard or this nuclei, they are looking like something which is strongly correlated random numbers with which the levels are repelling each other. They are correlated because if they were independent, they will look like the first column. They are in some sense correlated, and they seem to be avoiding each other, and there is more rigidity. But it is not as rigid as this uniform distribution. Okay, there is more rigidity, whereas for the integrable case, it looks like quite the opposite of what we would expect. The integrable cases, the spacing looks as if the energy eigenvalues are lying randomly and independently randomly, whereas for a chaotic system, they are correlated. Okay, kind of one can understand why that is so, but at the face of it, when one first comes to it, it looks kind of bizarre. Okay, so I'm going to, in the next 10 minutes or so, introduce some central characters in random matrix theory. So, in fact, you can do a lot surprisingly with 2 by 2 matrices. What exactly are random matrices? Because random matrices form a kind of an important statistical modeling of quantum chaos. So let's take a 2 by 2 matrix, which is real symmetric. Okay, so it's all real numbers, and therefore Z and Z are the same, X and Y can be different. And let's say that they are all independent random numbers, and they are distributed in the following way, that X is distributed 0 mean and normal distribution, 0 mean, sigma squared, standard is the variance. And similarly, y is exactly same. So that's this diagonal entries. The off diagonal entries have this variance is 1/2 of the variance of the diagonal entries. Otherwise, they are all zero centered normal numbers. Now, I've taken this the following way so that I can write the joint probability distribution of these matrix elements as probability of x, y, and z just independent like this, right? So now, now this fact that there is a 2 there comes into play. You can take out 1 over 2 sigma squared, and you can write this as x squared plus y squared plus 2z squared. This combination is also the trace of the matrix square. This 2 here, so that you get this 2 here. And that 2 is there, so that you get trace of m squared. Why what? That's what I mean. So that I can, you see the difference here when I'm. Yes. Okay. So the joint probability of distribution of this is trace m squared, and therefore the probability of finding the matrix in some interval dx, dy, dz is just given by this. Okay, this is the probability of finding that. Why should we have trace m squared at all? Is because when we write a matrix in some, and then you take some random numbers here, it should be such that one of the desirable characteristics, whatever you derive from this as a random matrix, should be independent of the basis in which you are expressing that matrix. It should be basis independent. If it is basis dependent, then there are so many different bases, you can't really compare one from the other. So now this trace m squared is something which is independent of whatever basis you may have. The trace m squared is independent of that basis, and therefore this is said to be an invariant ensemble. So what does that mean? More formally, you can take any orthogonal transformation of this matrix M, you'll get M prime. So O is orthogonal. And then you have different entries here, x prime, y prime, z prime, x prime, y prime, and z prime. And the volume element remains the same because it's an orthogonal transformation. And also, because it is trace m squared, P of m is equal to P of m prime. And therefore, whatever basis you may choose, this the probability of finding this matrix does not change. So these are invariant under these orthogonal transformations, and therefore this is called an orthogonal ensemble. It does not consist of orthogonal matrices. Please note, it consists of only real symmetric matrices, and it's called Gaussian, of course, because the elements are Gaussian distributed. Gaussians are also very natural, otherwise you won't get trace of m squared. Okay, so actually Gaussians are in some sense, again, from rotational symmetry. So we can have a more formal, in the formal definitions of, in introductions of random matrix theory, you may require certain characteristics and then derive this as the unique distribution. I have gone the other way around and kind of motivated why this is something which is useful to have. Okay, in the sense that now you can solve for many things from such an ensemble. What exactly do we want to solve? We might want to look at, for example, eigenvalues. So you have this matrix, which is a random matrix, or you have an ensemble of random matrices. So you have an ensemble of eigenvalues which are coming out of this. What are the properties of these eigenvalues? And it has eigenfunctions. What are the properties of the eigenfunctions? So you can actually go from x, y, z in this 2 by 2 case to lambda 1, lambda 2, and theta. Theta will be essentially cos theta, sin theta will be the eigenvector, one of the eigenvectors. Other vector will be sin theta minus cos theta, orthogonal to that. And then you can make some Jacobian transformation from x, y, z to these, and that is this 3 by 3 matrix, whose determinant turns out to be simply the difference of these eigenvalues. And therefore, you can go from here to a joint probability distribution, or this is a probability distribution of the matrix M, to be written purely in terms of the eigenvalues, which is possible only because of, again, this trace m squared. Okay, so trace m square you can see immediately gives you the sum of the square of the eigenvalues. This factor here, lambda 1 minus lambda 2, is coming from the determinant, transformation of the determinant. Okay, so this is called a Vandermonde factor, and it tells you that the probability having two eigenvalues which are close by is nearly zero, which is again understandable. You're taking a random matrix, why should you have degenerate eigenvalues? So probability of finding degenerate eigenvalues is zero. And it is exactly going like this. And notice that there's no dependence on theta, which means that this theta is uniformly distributed. This is precisely what we assumed actually there for when we described eigenstates, and we said it's uniform except for the normalization. So this is actually reflecting that. Okay, so this is now the joint. You can ignore the theta, which is the distribution of the angle or the eigenvalue. So the eigenvalues and eigenvectors, they separate, and the eigenvalue distribution is given by this, lambda 1 minus lambda 2 times that. And so from this you can derive, this is the spacing distribution. For only 2 by 2, you have only one spacing. So the spacing is given by lambda 1 minus lambda 2. You can easily do this integral, and you will find that this is this by, if you require that the mean spacing be 1, then this is the function from this. This is how Wigner derived this thing, and it's called a surmise because you see he didn't use any n by n matrix at all, yet this is very close to the large n exact result, which was derived much later by Dyson and Mehta. So it's a very interesting thing that that 2 by 2 random matrix gives you something for an n by n random matrix to a very good accuracy. So there is supposed to be a linear level repulsion because s is to the power of 1. And it's potentially valid for time reversal symmetric system because we assume that this was a real matrix. Yeah. Huh? Yeah. It's a more complicated expression, but it is approximately this, to a very good approximation. So for, in general, an n by n real symmetric matrix, that is the Gaussian orthogonal ensemble, with diagonal elements from this normal distribution, zero-centered, sigma square, off diagonal elements, half of that variance. And then you can write it exactly in that form which I said, e to the power of minus trace m squared. And so the eigenvalue distribution of that has this trace m squared factor, sigma lambda I squared. And this is coming from the Jacobian transformation. It's called, that's the Vandermonde determinant. It is the product of all the pairs of eigenvalues, I less than j. So this is the joint probability distribution. The Zn is a normalization factor from that, for which the exact things are known. So you can derive a whole lot of random matrix results based on this, and this is where the correlations come. So it's a strongly correlated spectrum because of this Vandermonde determinant. They repel each other from this. How to generate it actually is very simple. You take a matrix A, which is fully IID, n0 sigma squared, and just do A plus A transpose by 2. A is called a Ginebra ensemble because that's not got any structure of a symmetric matrix. But if you take a matrix and take its transpose by 2, obviously that's a symmetric matrix. Okay, A itself is non-Hermitian, but H is Hermitian. Okay, so, and if you ask what is the eigenvalues themselves, how a single eigenvalue is distributed, you can integrate out the others, and you will find the so-called semicircle law of Wigner semicircle law. You can easily see kind of why the eigenvalues. See, let's do this. So trace m squared is the sum of the eigenvalues squared. Now that is in terms of the matrix elements, it's the sum of the square of the matrix elements. Now we know how each of them is distributed. It's a normal distribution. So it's approximately, you can figure this out. N is the dimension, small n is the dimension. There it was large n. So it's going as n square sigma squared. But this itself, if you say that all the eigenvalues are, there's nothing, I mean, the scaling is the same, then this is going to scale as small n times lambda I squared. And so lambda I is going to scale as square root of n sigma. It means that if you take a 100 by 100 random matrix, the eigenvalues you're going to get are going to be of the order of 10, okay, if sigma is 1. And you can find out, therefore, if you scale this by square root of n sigma squared, you will get a distribution like this, which is lying between -1 and 1, and that is like this. It's not, it doesn't look like a semicircle, but it's called a semicircle law. This is not very useful because if you take a real system which is quantum chaotic and find out its density of states, that is precisely what is eigenvalues, it is not distributed according to the semicircle law. Okay, what is distributed, however, are things like the spacing and so on. So the density of states itself is too crude in some sense to capture the dynamics, and therefore it does not reflect the spectrum of real Hamiltonian systems. Okay. See, this is what is this? This is telling you the eigenvalue distribution, density of states of a random matrix. But let's say that you take some quartic oscillator or something which is chaotic, or this billiards, and if you find out its density of states, it will not be this. It will not be semicircle. However, the spacing distribution will be Wigner and all that. Huh? No. It's not universal. It will depend on the Hamiltonian. Although these distributions are themselves also interesting, they come in other contexts. But for example, for those of you who are already doing a lot of many-body physics, the SYK random kind of model will form something like a semicircle. The density of states will be looking like a semicircle. There are derivations for the SYK. Yeah, so in a way it's already a random matrix, although it's not exactly, there is a difference between, it's a more structured random matrix, but you're right, it's not something which is, it's already, yeah. So for the case of Hermitian matrices, so for GUE is a unitary ensemble, you require that it be invariant under unitary transformations, not orthogonal. This allows for time reversal breaking systems. And then if you do the, again, trace m squared, but m is now complex, its real part and imaginary parts are IID normally distributed, and it's given by this. You can derive, again, using just 2 by 2 example, you can derive the Wigner surmise for that. And the important difference is it goes as s squared e power minus s squared. So there is more level repulsion because time reversal is broken. So we have already encountered for the case of eigenfunctions that time reversal breaking makes it more delocalized. Time, in terms of eigenvalues, it makes it more repel more. So if you take Riemann zeta zeros and find out the spacing distribution of this, it will be remarkably close to this. Or if you take a system which is breaking time reversal, you can take the standard map and do things. Or you can put some magnetic field in some billiards, breaking time reversal, ensuring that time reversal is broken. May not be always easy, but you can do that. Okay, so I should also mention the circular ensembles because we have been dealing with things like unitary matrices, Floquet systems. So there is no Hamiltonian there. So, by the way, so all of these things which I'm introducing, they are all models of Hamiltonians. If you don't know the Hamiltonian is looking, or even if you know the Hamiltonian and that of a chaotic system, it looks like that it's like a random matrix. The spectral fluctuations look like they are random matrices. But we have Floquet operators, we have unitaries, and therefore you can also define unitary ensembles. Unitary ensembles are random unitary matrices from the so-called circular ensembles. And again, there are 3 main ones: circular orthogonal, unitary, and symplectic. For example, if there is, the only constraint is of a matrix U is that it be UU dagger is identity, you can think about this as giving you the probability distribution of the elements of that unitary matrix. It's more correlated because, for the case of a Hermitian matrix, we could just define they're all independent and IID distributed. But in the case of unitary, every column has to be orthogonal to each other, and therefore there's more correlation built up in that, and therefore that's more difficult, but that's how you would describe that. The eigenangles of this, or quasi-energies, are distributed like this. So it's a very simple formula again. It looks like just the van der Monde determinant, lambda I minus lambda j minus lambda k. The lambdas are now on the circle, e to the I theta j. To the power of beta, this beta is a convenient way I could have also written for the Gaussian ensembles. If beta is 1, it is time reversal symmetric. If beta is 2, it is time reversal breaking, or CUE. And if it is 4, it is symplectic ensemble. I must say that calculationally, the most simplest ensemble is CUE. And in fact, when one says typically that, okay, let's pick a random matrix let's pick a unitary matrix at random, they mean the circular unitary ensemble, sometimes called a Haar measure on UN, because the space of unitary matrices is some large sphere, and you're taking every point on that sphere as a unitary matrix, you're kind of sampling that sphere uniformly. And so that's called a Haar measure. So they model Floquet operators, scattering matrices, random unitary gates. People construct circuits, random circuits. They would pick gates randomly. They would all be coming from such ensembles. What is interesting is that fluctuation properties, like again, if you look at the spacing between theta I plus 1 and theta I, like this theta j plus 1 minus theta j, you can just multiply by n by 2 pi because there are n eigenvalues in 2 pi angle. So this will give you something with the spacing which is roughly 1. Average spacing is 1. So you just scale it like that, it will follow the spacing distributions of the Wigner surmise for large n. So for the Gaussian ensembles. So although the circular ensembles differ in important ways, as far as fluctuations like nearest neighbor spacing distribution or even the eigenstates are concerned, they are the same as that of these Gaussian ensembles as well. And by the way, there is a very vast universality which people have proven for random matrices. You may ask, it seems to be very particular that I should take normal distribution and that too each of the elements have to be this fine-tuned. What if we take some other distribution or it's not so fine-tuned? People have shown universality results for large n that the distribution of the spacings distributions as well as the Wigner semicircle law and so on, a lot of these things are robust against such changes. It's just that these, which are called invariant ensembles because of this underlying group structure, are solvable in some way. We can write down easily joint probability distributions and so on. Beyond that, it's not easy at all, but there are many interesting, nice books which are there on random matrix theory recently because it's of very wide applicability. It's not only quantum chaos, it's applied through vastly in physics, from random matrix theory, from nuclear physics to various other things, and beyond physics, econophysics, and a lot of statistics and so on. Correlation matrices, and in fact, even before Wigner, there was study of correlation matrices, random correlation matrices by Wishart in the 1930s. Okay, so let me go beyond the density of states. I'll introduce this important quantity also, which is widely used now in many body physics as well, something called the spectral form factor, which talks about what happens to two eigenvalues, okay, Ej minus Ek, let's say this difference, how are they distributed? How is this distributed, Ej minus Ek for all j and k? Those are called 2-point correlations. And here is a simple quantity. You just take the trace of a propagator. So you'll have e to the minus I energy eigenvalues time. modulus squared. It's a complex number, you take modulus square of that, and that can be written like this. This need not converge or something, but let's assume that you have done something to make this well-defined object. For example, if suppose it is a unitary operator like the standard map or something like that, Baker's map, it's only finite dimensions. And trace of the, now the small n is time for us, trace of u power n is giving you the sum of the eigenvalues, e to the power of I eigenangles. And we take modulus square of that. Okay, we can normalize by dividing it by n. So let me not divide by n, okay, it's just modulus squared. So let me call g of tau when you divide by n, okay, and this tau also we can divide time by capital N. All right, so with all of those things, we can ask how these quantities are behaving for various ensembles that we have introduced. So for the circular orthogonal ensemble or for the Gaussian orthogonal ensembles, they behave in a different way for tau less than 1 and tau greater than 1. This tau is t by capital N. So this is a time scale which is telling you it's as large as the system time scale. As the Hilbert space dimension. It's called the Heisenberg time scale. So that's the largest time scale beyond which any quantity or it will, all the levels are resolved. The discreteness of the levels are kind of resolved. So it's a very large time scale. Okay. The case of the unitary ensembles where time reversal symmetry is broken is very simple. It looks like just tau. So it's just a linear ramp and then it's 1 after this time, which is tau is 1 or t is capital N. It's just a linear ramp. And for Poisson, it's just 1. It's flat throughout for tau greater than 0. So you can again see that it will be quite different for integrable systems, time reversal symmetric systems, time reversal breaking systems. And each of these things you can kind of argue. It's quite easy to see why they should be 1 for a Poisson, where you can assume that everything is independent random variables, and therefore it's 1. Okay, whereas the interesting thing is this tau, for example, and for this tau less than 1 behavior, this is this where all the dynamics is coming. Okay, so the Poisson levels are uncorrelated, and yeah. Good question, because I find that in the modern literature on many body physics, many body systems, people attribute it to some very new papers. They are derived in by Dyson and Mehta. They're there in Mehta's book in the 1960s. Okay, I'm on record, so I don't want to say something wrong. But it's done by these kind of people, not any time. Could be Dyson.
No, means to get and another thing, is it possible to understand that level repulsion and tau, that dependence, or that part is also easy to explain, that level repulsion is related to that linear in tau?
Yeah, in a way. I mean, the small time behavior is related to the smaller level correlation. So that it is going as tau, here it will be going as 2 tau and so on for small tau, the spacing of that. They are kind of related to that. So you can take a Fourier transform of this. Fourier transform of this gives you a delta function on all Ej minus Ek. It's not directly spacings, because spacings will be only nearest neighbor levels. This gives you density of all spacings. Okay, so you'll have to kind of infer from that. It's not directly giving you only nearest neighbor spacings. Okay, so now let's use the models which we have introduced in the previous lectures and derive them and calculate them. When you do it, that is, you diagonalize a standard map, you find out eigenangles, you calculate this, you will find that it doesn't fit any of these. You will find a highly fluctuating curve, And that's because this quantity is famously not self-averaging. So you have to do something. This is an average over random matrices. So if you take a thing like a standard map, there's no random matrix there. So actually it will not turn out to be like that. Unlike the nearest neighbor spacings and so on, for which you don't have to do any averaging, this quantity you have to do some averaging. For example, I have taken an average over k. This parameter k, I've taken an average over a small range so that the dynamics doesn't change a whole lot. For example, here I've taken k to lie between 0.1, 0.9 and 1.1. I've taken 20 values of k between that and I've averaged this quantity over that. Now, this is n is 426. I have broken parity, but I have kept time reversal in this case. And what you can see is this fluctuating quantity is this blue fluctuating line is the spectral form factor. It's highly fluctuating, but you can see that it's fluctuating around 1, which is the Poisson value, and it almost immediately goes to 1. Okay, and if we break time reversal, that is this plot below immediately. Somehow this thing has become, I think I've talked too long. You can see some weak thing here. So you can see there's not much difference between this. It's still k is 0.9, which means it's not chaotic, remember, 0.9. So it's looking like Poisson, where it is almost 1 right from the beginning of time. This is time divided by n. And I'm going from time 0 to 2n. So 2. So that means that I'm going till 2n, about 800, more than 800 times. Now this is for the case where I've kept time reversal symmetry, the top right corner. And you can see that this red line is what I have here as this curve here. So it fits pretty reasonably well, this highly fluctuating quantity. And here I've taken k to be 10, around 10. Okay, 20 points around 9.9 to 10.1. Where you know that it's highly chaotic. We have already demonstrated that kind of thing. So you can see that it for average out over k, it would come. If you don't average over k, you won't see any of these structures. And here I've broken time reversal by putting one of those fluxes to be non-zero. And you can see that it's a linear ramp till exactly the time 1, the scale time of 1 or the Heisenberg time, after which it flattens out into that. This is Poisson. This one is k is small. K is around 1, where it's not fully chaotic at all. And so it does not matter. It doesn't see, it will be like spectral form factor will be 1 everywhere. It means that if you just take one realization of that, it will not look like the average or ergodic. It is not ergodic that way. Which is self-averaging. Like for instance, any of these things, we've looked at this spacing distribution. I didn't plot for a single standard map, but if you do, you will find that it will fit this Vignyana sum. You don't have to do any averaging over k. It will form that. Or if you take this spacings here, I showed you these participation ratios. I didn't do any k averaging. For a given k, I will find here, although I do average over all the eigenstates, okay? But even if you take a single eigenstate, there will be fluctuations, but it will be very strongly centered around this, and as n increases, that fluctuation will decrease. These are not the case with the non-self-averaging quantities. Well, that's a slightly more involved question, which I don't think is... So there is a lot of actual dynamics which is going on here. So if you... dynamics meaning actually the people, I mean, there are people who say that they have proved random matrix or the BGS conjecture that random matrices and chaotic systems are having the same kind of spectral features by actually trying to derive this using semi-classics. So these things are coming from some properties of periodic orbits and so on. Okay, So this has to do with fluctuations in the periodic orbits itself. So there's a lot of dynamics which is there in this, which is not. So that means that it's not universal till you are doing this, till you are doing this average. K. So there's a range of K. I just see to it that it's not like a senseless value like 9.9 to 10.1. It's chaotic. There is no, I mean, it's roughly the same amount of classical chaos. Huh? No, no, no. That's not because of that. Here for, yeah, no, it's not because of that. But actually we're not very far off. This is a 2-point correlation, that's a 1-point correlation, that density of states. Okay, so now I have 15 minutes. I will go into some many body aspects, if I may. Is that fine? Okay. You waited long enough for that. Okay, so I'm going to mostly talk about many body. When you look at single particle thing, you look at eigenfunctions and so on, there is one basis and it can depend on the basis that you have taken. For example, we saw participation ratio. Depending on whether it's momentum or position, it could have different behavior, except when it is fully chaotic. Then there is many particle physics. At least you can look at quantities which are independent of single particle basis. Okay, because that entanglement is a very useful quantity that way. And well, I don't have to tell you that entanglement is something which is widely used now. It's a unique quantum correlation and so on and so forth. And kind of philosophically, the whole contains the parts. That's how we think about it. If you give us the whole state, like a state of two particles, position momentum of two particles, it implies the knowledge of single particles, Q1 and P1. This is not the case in quantum mechanics. Quantum mechanics, if you give a full, if you know the states, let me put it this way, if you know the states of the constituent particles, Q1, P1 and Q2, P2, you know the state of the whole. But in quantum mechanics, this is not necessarily the case. Knowing the subsystem states does not give you the full state knowledge because of entanglement. So what is entanglement? Very roughly again, 101. A product state like this, if you take two particles, let's say qubits in which the states can be 0 or 1, then you can think about it as up or down or whatever it is, some binary thing. So if it can be written as a product like that, then it's unentangled. For example, this is the second state is also unentangled because it can be written as 1 plus 0 tensor product, 0 plus 1, and therefore this is also an unentangled state. Entangled states cannot be written as tensor products of pure states. You would call that, for example, that's the famous singlet state. You cannot write this as a product. So if you take a 2-qubit state like this, a qubit is just a 2-level system. That's the most general possible state. And you can easily see that if you write this as a matrix, A00, A01, A10, A11, it's a 2x2 matrix. If its determinant is not 0, then it's an entangled state. So you can see that this is going to be typical. So entanglement is going to be there generally. So an entanglement cannot be created locally. You can't apply some some unitary transformations locally on one qubit or the other qubit and create entanglement. It can decrease by some local operations like measurements. You can't increase it. Okay, so this was known to Schrödinger. The whole is in a definite state, whereas the parts are not. So how does one measure entanglement? Here is a pure state of two particles, bipartite. So you call particle A and particle B, or system A, system B can consist of many particles. and of dimension n and dimension m, let's say n is smaller than m. So a pure state can be written as this, sum like this in some product basis I alpha. So yeah, so that's a bipartite state. Let's say that this is some orthonormal basis of A, orthonormal, the Greek is the other orthonormal basis. So again, you can write this coefficient as a matrix. So it's an n cross m matrix in general. Okay, so it's a rectangular matrix. And then how do you define the state of a particle A? You trace out from this density matrix, total density matrix psi AB, psi AB, you trace out particle B. And you call this the density matrix corresponding to the state of A. So if you have access only to A, only row A gives you all the information. You can calculate the observables and so on from row A. And that in terms of this matrix capital A can be written simply as A adjoint. Okay, so you can see immediately that it's a positive matrix, positive semi-definite. It can be zero eigenvalues, but it's positive. Its expectation value in any state is positive or equal to zero. And this will be entangled, the state will be entangled if this density matrix itself is not a pure state. Because if this was a pure state itself, psi AB, then tracing out the other one will be still a pure state because it's a product of pure states. So as long as this density matrix is not a pure state, that is trace of rho square is less than 1, then the state is entangled. So you can measure entanglement by this, by looking at how mixed is this reduced density matrix rho A. For example, one of the standard measures is the von Neumann entropy of this density matrix rho A, which is calculated like this minus trace log rho A log rho A. If you diagonalize rho A and get these eigenvalues lambda I, it's simply given by this sum. Okay, where there are n eigenvalues. Remember this A is a square rectangular matrix n cross m. A adjoint will be a square matrix n cross n. And it will be having n eigenvalues. Typically, all of them will be 0. If you calculate rho B, reduced density matrix for rho B, it will be an m cross m matrix. I'll leave it as an exercise for you to find out what it is in terms of A and A adjoint. Basically, it's A adjoint A, but it's not exactly that. It will be an m cross m matrix, which will have exactly the same eigenvalues, non-zero eigenvalues as rho A. All the others will be 0. It will be padded. Okay, now the entanglement in this pure bipartite state is measured by the entropy of these reduced density matrix. It does not matter whether it's rho A or rho B. They share the same eigenvalues, non-zero eigenvalues, and therefore their entropies are the same. And that is the entanglement content of this pure state. It's 0 for unentangled states and log n, where n is the smaller dimension for maximally entangled states. It cannot be larger than that. So all the entanglement lies between 0 and log n. Okay, so now you can ask, we have talked about random states and so on. What are suppose that this was a random state. This AI alpha followed that distribution which I showed you at the beginning. Delta sigma AI squared equals 1. What will be the reduced density matrix of, what will be the eigenvalue distributions of that, and what will be the entanglement of such a random state? So in fact, you can construct such an ensemble of random matrices which have the form AA adjoint, where A is an n cross m random matrix, elements real and imaginary parts normal distributed with 0, 1. And you can, now this is a random matrix, random positive trace 1 matrix is an model of a random matrix, random mixed state. And you can ask, what are the eigenvalues will be now random? What will be the distribution of the eigenvalues? There's a joint probability distribution of this, which can be derived in similar way that I've derived for the other one. Here, this is telling you that the trace has to be 1. So delta sigma lambda I equals 1. This is coming again from the Vandermonde kind of determinant, lambda j minus lambda k to the power of beta. And again, beta takes the value 1 for time reversal symmetric, 2 for unitary, and 4 for symplectic. And you have this factor which is replacing that exponential factors. You have these products, but this one is not creating any correlations. All the correlations are coming from this Vandermonde again, and also weakly from this delta function. Now, if you ask what is the distribution of a single reduced density matrix eigenvalue, these are now reduced density matrix eigenvalues. It's called the Marchenko-Pasture law. It was derived by Marchenko-Pasture in 1967. So this is the equivalent of the Wigner semicircle law. And for the case when m is equal to n, it has a simple form, 4 minus x by x, where this x I have normalized by multiplying by capital N. Okay, so now that's a little bit fast, but basically let me, yeah, 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 yeah. No, random states are just a random model. We expect them to be valid for chaotic many particle systems. Yeah. It will not be Marchenko-Pasture. That's all I can say. Nothing universal again. It's not universal. Okay, so now what about the average entanglement? So you can find this. This is the distribution of the eigenvalues of the density matrix. You can calculate this and find out the average of that from this distribution. Quite remarkably, for beta equal to 2, you can do this exactly, and there is a very nice formula for this. It was derived by Don Page in 1993. And this is exact for any m and n, but for large dimensions n and m, it's approximately given by this. Now this m is a larger dimensionality of the two particles. You can see that if n is equal to m, this is log n minus half. Now log n is a maximum possible entanglement. So you can see that actually typical states, random states, are nearly maximally entangled in some sense. That the average entanglement is, log n is a maximum, it differs from that only by a factor of 1/2. And if m is going to infinity, this is going to 0 and it gets maximally entangled. So it has a very simple interpretation. You can think of m as the other subspace, which is like a bath or something, is becoming very large, and then the subsystem entropy is tending towards the maximum possible. Okay, and then it's getting maximally entangled. This is beta equal to 2. Time reversal breaking. Time reversal breaking. Okay, so in fact, when you take any typical state, if one says that, okay, we have here a Hilbert space, the Hilbert space is typically complex, and therefore, when one says we'll take a typical state from that, it is complex, and therefore it will be like time reversal is broken. It's a different, so it is still true that it is log n minus something which is more harder to find. This exact formula is harder to find. But all of these statements are true. Typical states are nearly maximally entangled, all of that. But it is less entangled than, again, a time reversal breaking system. Okay, so here I'm showing you some results of ours from long ago, as you can see. I've coupled two standard maps, which we are familiar with. K1 is the parameter for one standard map, 0.1, 0.15. So the uncoupled standard maps are nearly integrable. I have not shown you the full Hamiltonian. You can see all of that here. This is some coupling between them. So it now becomes a 4-dimensional map classically. And if you look at the eigenstates of them and then look at their average entanglement across the spectrum, this is how it changes with the coupling constant B. So it's 0 without any coupling, however chaotic your system may be, because it's unentangled. And then it grows and it saturates as this coupling strength increases, and you have full classical chaos, which corresponds to a fully entangled system also in a quantum mechanical sense. And this value here is exactly the log n minus half value that you find. This is for different values of capital N, 15, 20, and 25. So log n minus half is increasing. So this was some of the early works which kind of showed that random matrix entanglement for random states is found in dynamical systems. And this is another system where this is now a time evolving state. You start from unentangled state, this is time, and this is the page value. And this is, by the way, this is called a page value after Don page, this particular value. So it approaches the page value after some time, and that's kind of a thermalization. You can also start from a maximally entangled initial state. You see a slightly dotted line there. Actually, it starts from there and it decreases to this typical value. It gets unentangled to this random state value. So again, so you say that chaos creates highly entangled random states. Okay, and oh, this is the von Neumann entropy. Oh, this one. This one is, I think, it's a kind of a, if I understand, it's a kind of a log plot to kind of show that this is growing as some power law in B. If I remember right, it's kind of an oldish paper. But there is also, if you look at this paper in 2002, we compared the distributions of these reduced density matrix eigenvalues to Marchenko-Pasture. So you can see a comparison to this. So that kind of thing has been done. Okay, so I think I'm at 4:30. What shall we do? So I think I will, tell me how long, 5 minutes? 10 minutes is okay? Okay, so let me try to tell you something about, because actually what is interesting is that there is entanglement, and but there's more to entanglement than meets the eye. If you take, okay, so what here I'm saying is that if A and B are maximally entangled, I have a bunch of now many particles, not just two particles. If A and B are maximally entangled, they cannot be entangled with any other particle. So this is called monogamy of entanglement, unlike classical correlations. So if A and B are qubits, like two-state systems, like spin-half particles, then if they are maximally entangled, like they form a singlet state, it cannot be entangled with anything else. And the measure of two-qubit entanglement, even in mixed states, is given by concurrence. I'm not going to go into that, but let me just say that concurrence measures entanglement between two qubits in any state, pure or mixed. Okay. Now, if you take a random state like this, we know that there will be a large entanglement between A, B and the rest of it, and therefore there will be a small entanglement between A and B because of, again, monogamy. So you can expect random states to be something where entanglement is spread in some multipartite manner, but there is no entanglement between small subsystems because of the monogamy of entanglement. Just to drive home the monogamy part, if you just take 3 qubits, for example, here is the state of up, up, up plus down, down, down. This is the GHZ state. If you calculate the state of any 2 qubits, it is separable. You can actually write it as some combination of unentangled states, as some convex combination of unentangled states, and therefore it's considered to be separable mixed states. And therefore, no two particles are entangled with each other, but all three are entangled together in something like a Borromean configuration. And in fact, that's how random typical states are. Entanglement is kind of spread out like this. So many body systems in quantum chaos, as said, is detected by random matrix properties of spectra like eigenvalues and so on. It leads to large multipartite entanglement, like entanglement of large blocks of spins with other blocks of spins. But it will lead to zero or small entanglement within qubits. It scrambles information exponentially fast. That means that if you localize entanglement, let's say between 2 qubits like this, its final state, the entanglement will be distributed in a much more multipartite manner. It will not remain localized anywhere. It will scramble this information in a multipartite sense. So things like OTOCs are being studied these days to detect such scrambling. And they are coming from a lack of quasi-particles which drive subsystems to thermalization. Okay, so let's take an example, Hamiltonian, which is not a, so this is a tilted field Ising model. Okay, so it's an Ising model, sigma z, x and z. If you have only x or z, they are integrable. But if you have both x and z, it's a non-integrable system. So it's integrable in these two limits. And in fact, this is the kind of spaghetti plot which I told you. Again, you have to do a symmetry reduction and look at only a particular parity sector. Integrable point, 0, there's a lot of degeneracy. And this is the angle of tilt here. So theta equals 0. Theta equal to 0, you can see it's simply sigma z. So there are a lot of conserved quantities and it's integrable. At here, theta equal to pi by 2 is the famous transverse field Ising model. It can be solved by the Jordan-Wigner transform, that is this point here. It will form Poisson statistics at these points. Intermediate tilt angles, it will form a nearest neighbor spacing distribution, looks very much like a Wigner distribution. Now you can look at eigenstates of this Hamiltonian and ask for the entanglement properties. You will see that this is one integrable point, another integrable point. It increases, and this is non-integrable regions. It reaches large entanglement, again decreases at the end. This is entanglement of 1/2 of the spin chain with another 1/2. I'll call this multipartite entanglement. But if you ask entanglement of any two spins and then average it out over all pairs, that is this one here, it's calculating the concurrence, you can see that it's decreasing. And in the case where there is large chaos and large multipartite entanglement, it is actually small. This is a reflection of the monogamy of entanglement. Okay, so this is from an old paper from 2007. I'll skip what's happening to time evolution. Okay, so one of the examples of this which has been studied extensively is the many-body localization example, where you have a Hamiltonian such as this, which is integrable, the xxz model, and then there is a transverse field, or actually there's a disordered field, not transverse in this case, because anyway this has got all the directions in here. But this disorder is breaking the integrability of this point, and you will see again a transition which from an integrable model when there is no disorder, w equal to 0, w is the disorder strength here, to something which is non-integrable for w large but not very large. But w tends towards infinity, it becomes purely a model in which the disorder is dominating, and then it gets localized into this many-body localized states. So a supposed transition happens here. The transition itself is changing continuously exactly where this transition happens. But it's a very interesting case where, again, this is where there is a chaos or random matrix kind of thing. You can see that the spectrum is repulsing, is kind of repelling. And you will have a nearest neighbor spacing distribution like a Wigner to something which is a Poisson distribution in the localized phase here. This is some work done with Chomobera in Bombay, where we looked at the nearest neighbor entanglement, that is through this concurrence, and you can see a very different structure here. This is how the spacing distribution goes from that of random matrix to that of Poisson, 0.39. This is the around 0.52 to 0.39 for time reversal symmetric system. That is, this one refers to this ratio of spacings, whereas this is the nearest neighbor entanglement. It actually increases here in the ergodic phase or in the chaotic phase. It's very small, and here it's very large. So in the many-body localized phase, you have entanglement between spins and no large-scale entanglement. There are a lot of interesting experiments, quantum thermalization through entanglement in an isolated many-body system, which deals with Bose condensed gases, and in fact here it simulates a Bose-Hubbard model. This is a case of, in fact, since we talked about kicked systems and we use the spin models, we used the standard map. This is a kick top. So J, Y and JZ square kicking. So this has been realized using both circular cold atoms as well as in this paper through Josephson junctions. And so that's a more detailed thing. Let me skip over that. But you can see again, these kind of pictures which I've been showing, they have been, entanglement has been measured in this average entanglement. And this entanglement is small in the case where there is regular regions, and entanglement is larger where you have chaos. So that's roughly what I want to again say. But analytical solutions are possible in this case for small number of qubits, but let me skip over that. Okay, so I think I'll skip over the OTOCs. I just had these 2 slides, but I think I'll skip over that since it's 10 minutes already over time. So thank you for listening to a long thing. I think we spent a lot of time on classical chaos, diversified a little bit into quantum chaos, and even more less into many body physics and a little bit of random matrix theory. There's a lot of connections to black hole physics, scrambling in many body systems, out of time autocorrelators, quantum information itself. It's a very interesting question, field with a lot of interconnections and interdisciplinary field, and a lot of basic questions do remain unanswered. But I hope that I've conveyed that there are even simple models which you can play around rather easily and actually understand a lot of these things. So thank you. Yeah. Oh, you want me to go back? Yeah. W is the width of this disorder. So disorder lies between minus W by 2 and W by 2 uniform. That's sort of how it takes this. Strength of disorder. Huh? Yeah, basically W is 0, there is no disorder. So that's an integrable model. Yeah. So here, oh, so maybe this will help actually. What I'm plotting, what is plotted here, and this looks nice also, is that this is the entanglement between spin 0 and spin 1, entanglement between spin 1 and spin 2, etc. Okay, and this is time. I'm sorry, this is the energy. So we are looking at the energy spectrum, say 0 to 900 levels or whatever. And for each of these things, we are calculating this nearest neighbor entanglement or concurrence. And you can see that some of the pairs are highly entangled. Okay, this is for W is 6, highly, there's a lot of disorder. There's a lot of entanglement, whereas W is 1, this is in the chaotic phase, there is no entanglement. In the bulk of the spectrum, this is very small, 0, actually 0 entanglement. So this entanglement between 2 spins is developing as this disorder is growing. And exactly which spins are getting entangled depends on the exact disorder configuration. You can kind of understand that from some resonance argument. Here what is plotted is the average of this. So this is so we basically sum up along all these neighbors here, and then we are plotting this as a function of disorder strength. So it's very small for small disorder. That is this. So it's indicating that it's blank here, which means that entanglement is more multipartite. And then as this disorder is growing, it gets into a between 2 spins and so on. So in the disorder phase, some of the eigenstates are large concurrence. Yeah. So that concurrence value is sort of related to the localization length. So good question. So actually we did calculate some length from this, which is how the average nearest neighbor, how this concurrence between I and I plus k, how it is decaying with k. There is an exponential drop off, and that defines, in my opinion, that's a good length to be actually used. Whereas people do more heuristic things for getting this length.
I have a question because your transition is around 3. What is the reason for that 3? Because now it's formed much larger, right?
Now it is much larger.
So is it because of...
But you see, at that time when we wrote the paper, 3.2, we were consistent.
So now people have changed, you didn't change your plot.
No. I mean, come on, we are honest people. So that's what I think. It depends on how much you want to. You look at. This is actually total concurrence, by the way. We do some scaling. You can look in the paper. This is not a. This is looking something between 2 and 3. If you do finite size scaling, you will find actually, I forget now the number, but it's something probably larger than 4, if I remember. I'm not sure. But it's not as large as what it is now. It depends on the quantities which one is calculating, and various kind of localizations, and there could be phases. It might not be simple, one many body localized phase. And yeah, so I think one has to look at these states in many different ways. Yeah. Is what? Yeah, for the the distribution. You have what? Yeah. You can define actually. So you can have some function of M and a trace of that. For example, this is actually the whole matrix models. A lot of string theory, field theory guys, they do these matrix models. Actually, also people who are modeling proteins and so on. You can have a much more complicated function than just M square trace of that. You can have some potential like N square plus M power 4. You're talking about determinant, but I'm giving you some other kind of invariance based on trace. So the whole thing is whether this distribution which you calculate can be based on whatever invariance you want. It should be invariant under the distribution should be invariant under under orthogonal spaces, and also it in this case it's built from independent entries. Yeah, so they are made from independent. I did say that. It's made from independent entries. So not correlated. So you can have some other kind of distribution, but this is what is found to be actually solvable and rather relevant. But the other ones, like this more generalized matrix models, you can write down easily because of that thing. You can write down some joint probability distributions easily. But what is exactly the matrix, how you construct random matrices which give you this is not clear. You'll have to use some other Monte Carlo and so on to. If you just give me some expression for the joint probability distribution of eigenvalues, now you go back and say find matrices which will give me that. That's harder. Yeah. Well, I didn't. I mentioned it. How do I what? Measure theoretically, or I mean, kind of. So then you're asking me to complete my talk. So it's actually rather simple idea, which goes back to some 60s but it got a major revival in recent times because of this work of Maldacena, Schenker at Stanford. Let's take a classical Poisson bracket between x at a time t and momentum at time 0. Okay, so now this is defined as Poisson bracket derivative of x of t with respect to x0, derivative of p0 with respect to p0 minus the other term which will vanish here. So this is actually just given by derivative of xt with respect to x0. So if you take the square of this Poisson bracket, it kind of tells you how much x of t is changing because of a change in x0. But going back to our early discussions, this is precisely if I change initial conditions, how much is the final condition changing? So this gives you, if there is chaos, you expect that this is increasing exponentially in time with that lambda being a Lyapunov exponent. Okay. So you can expect that Poisson brackets kind of measure a Lyapunov exponent. But we also know that Poisson brackets quantum mechanically are simply commutators. So you can calculate some object like this. Take some operator A and find out its commutator at different times. Here I'm calculating x of t and p0, but here I'm calculating the same operator. Doesn't matter. They will not commute at different times, typically. So you can find out how much they don't commute by finding out the magnitude of this commutator by doing something like this, for example. Take that joint. So this is a norm of that matrix commutator. So this is some scalar function of time, and see how that scalar function is changing in time. Now you can, if you work this out, you will see that it's a difference of two quantities. One which depends on trace of a squared and at squared. And here the time and the two times at 0 and t are just occurring next to each other. This is like a normal correlation function. And I've discussed correlation functions also a little bit in the in the resonances and all that. Here we have a more peculiar correlation involving time 0, 0, time t, 0, time t again, and 0. So this is said to be a out of time order correlator because the times here are not ordered. So this is where the time out of time order correlator is concerned. But you can see it is very closely connected to how the commutators grow. And if this is growing exponentially in time, in the quantum case, you can extract something which is looking like a quantum Lyapunov exponent. So that's the idea of this. You can calculate it for various quantum models. It need not be SYK, field theories, black holes, all kinds of things. Here I've calculated it for this kick top, which is like a standard. You can calculate it for standard map also, by the way. So people have done that. But I've here shown it for this kick top, which is also finite dimensional. I showed you the Hamiltonian or the unitary operator. It's a commutator between angular momentum Jz and Jx at a time n. They don't commute. So in this case, the log of the out of time order correlate, this one I've shown as a function of time n. You can see a linear growth of this, log of this. So this is indicating the exponential growth in time. So this gives you a kind of Lyapunov exponent. And this is for different system sizes. And it saturates here at a time which is exactly the Ehrenfest time. I've also discussed the Ehrenfest time before. So this is the Ehrenfest time, which is this log of 1 over h by lambda. So you can extract something. In this case, this exponent will look pretty close to the classical Lyapunov exponent. But that's also not very surprising because we said that till the Ehrenfest time, there is quantum classical correspondence. But it still quite depends on these operators and so on. And there are some interesting aspects to this difference between out of time order and this two time order kind. So yeah, so this is out of time order correlators, which people got excited because it kind of defined a Lyapunov exponent. But actually, if you see something like the tilted field Ising model, which there's no classical limit for this, and you calculate the out of time or the commutator between, let's say, spin at one site and another site at different times, it turns out that it does not exponentially grow. It grows only polynomially in time. You can't extract. So there is, mostly it's understood that only in models in which you have some large n limits or semi-classical limits, you have this exponential growth in time. But so for instance, if you have large spins rather than spin half, you might find some exponential growth. So still, I would say that people haven't found something like this exponential growth, even for non-integrable, like spin half kind of systems, which people have studied, although you can find non-integrability, Wigner distribution, all of that kind of things. Yeah. because it all becomes zero. No, it's finite. This thing.
So the classical one is still leading the lambda t.
You have to take some modulus and so on. When you are doing some average, you have to take some kind of modulus. So it's better because otherwise, delta xt, it can, yeah, I mean, it's good to take a modulus, both in classical and in quantum. Where do you want me to go? Oh. Yeah. Well, I think some of these things are for some condensed matter guys like to talk about quasi particles. So um, I did not show you that, but okay, let me probably say something. Where do I have this? Yeah. So this is one slide which I did not talk about. So let me talk about that. Here, what I'm doing is taking an initial state, which is a product state of all qubits except two of them, which I maximally entangle. And then I'm putting it through a spin chain of 10 spins in which there is both this longitudinal field and transverse field. So it's non-integrable typically. But here, this angle is 1/2. So this is integrable case, transverse field model. This is time on this axis. This is entanglement between two qubits. You can kind of see that the entanglement is growing, it's spreading after some time to all the things, and then it's recovering the entanglement. Here, the entanglement is more or less frozen between these first two cases. This is also integrable, it's near the pure Ising model, that is not transverse field. This one is in the integrable, non-integrable regime where this dies away from this. So if you have some kind of quasi-particle picture, what you will see is that you will see this entanglement. Like for example, you can do it for just the XX model, and you do this. We have done this kind of things. You will see a very nice picture where this entanglement is actually traveling to the right, reflecting, and then it's kind of diffusing and it's going there. So you can kind of think about it as if there's a quasi particle which is moving around in that situation. Whereas here you don't have that because of this. Like for example, all these spin waves and a few magnon excitations. Those are like quasi particles. Here they have all been destroyed.
So I don't know what you call tilted field, like
Tilted is when you have both this angle theta is not 0 or pi by 2. Yeah.
any more question? So if you let's say you have some many body chaotic transfer. So at most there is one sort of one realization of the ensemble that we are talking about. And so there is apparently no reason to expect that a single element from that ensemble will reflect the same statistical properties.
As that of a random matrix.
Yes,
Yeah.
that's sort of a random matrix ensemble. But yet it seems to do as far as the level spacing is concerned. But you also said it doesn't do for the eigenderivative.
Only for the density of states it does not. Yeah.
So why is that?
If you look at it semi-classically, right, a density of states is just given by the volume of the energy shell. Right? I mean, it's just delta E minus EI, it's a sum over that. And that is the first term which is coming in that. So the density of states, when you say density of states, what does it mean? It actually includes everything. I mean, in the sense that, oops. So a density of states, it doesn't matter, many body or that's the density of states. That's the definition of density of states. Strictly speaking, this has all the information. This has all the random matrix, chaos in it, and so on. However, this can be written in two ways. So it can be written as some average density of states plus some oscillating part here. So when one is talking about a density of states, as in that semicircle sense, one is really talking only about this. So this has this is like some volume of it's something like that in the semi-classical sense. Okay, so this is some volume of some object that need not have any universality associated. Universality all comes from this part, this oscillating part. Okay, so there'll be a density of states. So actually this is some spikes, bunch of. Out of that, we are constructing something which is some smooth curve, which is telling you. So density of states, as we can, is too crude something for in which you're going to. It's only a background kind of quantity. Unfolding is kind of based on this average. Yeah, so like in many of the quantities, I don't know, a lot of statistical analysis, one removes the average, right? The average might be something which is very system specific. It's the fluctuations which will be showing you interesting things. It's like that. And then there are outliers to all of this. There are exceptional cases. Even harmonic oscillators, they are integrable, uncoupled, separable ones. Their spacing distributions will be non-universal. There won't be Poisson. There won't be this thing. They'll have interesting number theoretic things. There is a whole field of arithmetic chaos where it can have deviations from these kind of things. But I would say that it's a very successful conjecture with a lot of numerical and analytical support so far. But what is interesting is even in the many body case, this is where there is no classical limit. See, we have been talking about quantum chaos from, let's say, standard map. We can always go back, find periodic orbits and so on, or phase space pictures. There's nothing here. It would be interesting if we can visualize eigenstates of this like we did for the standard map. I don't know how to do that. Thank you all for your patience.